Hello everyone, let us continue our discussion. So this is the 6th week and we are in lecture 1. This week we are going to learn stress strain relation. Okay, so the interrelation between stress and strain. Now, if you recall, we have defined 3D stress field as well as 3D strain field. So sigma ij, that's the 3D stress field, and it is defined by its component you all are familiar with. Let us write it down. So it's a symmetric matrix, as you can see on your screen. Similarly, we can also define strain field in 3D. And here again we have epsilon xx, then epsilon xy, or we can also define gamma xy. Recall engineering strain and true strain, and then gamma xz. Next row we have epsilon yy, gamma yz, and then epsilon zz. Right. Now the question is how to correlate these two matrices. That's what we are going to study today. Now before we do that, let us recall elementary strength of material and where we consider the 1D problem. So for 1D problem, the relation between stress and strain we all are familiar with. So stress is proportional to strain as per Hooke's law, and then this is the relation between stress and strain. Obviously, this 1D problem, now we have to extend it to 3D, where we have the stress and strain matrices are given, right? Now, before that, let us define the 3D material. So the material is homogeneous, elastic, and isotropic. So it is homogeneous, then elastic, and isotropic, right? I will explain each and every terminology in a minute. So it is isotropic. Now, what we mean by elasticity, it is very easy that if we apply some external force, the material is going to deform, and when we'll remove the load, it comes back to its original position, right? So that is relatively easy. What we mean by homogeneity, just imagine if we have the 1D problem for which we have already identified stress and strain and we interrelated them. So this is the test we discussed at the very beginning of this course. Now, if we consider, say, two different sections here and there. Now, material composition, say at section 1 and section 2, they are all same, right? Not only that, if I draw the cross section which may be of this shape, it's a circle for the time being, let us assume. So if we consider, say, a small element here and a small element there, and the material composition at these 2 points, they are exactly same. If that is the case, we call it a homogeneous material. Now, if I give you a different example where the material is not homogeneous, for example, concrete, right? So you have a concrete sample there. If you look at the microscopic details, you'll have coarse aggregate, then fine aggregate, then cements all over these cross sections. And if you take two different locations, as you can see in this case, the composition may not exactly be same, right? In case of steel, in case of any other material like aluminum, this assumption holds good. So the material is homogeneous, right? What about isotropy? Now, if you consider the same material and if you consider a point inside the material, so this is the material and I consider this point. Obviously, in our reference coordinate system, we have three different directions, right? So one is along this, another is vertical, and another is this way, right? Now, the material property, if it is same along all three directions, we call it a isotropic material. So we define homogeneity, elasticity, and isotropy, right? Now, with that description, so let us try to correlate these two matrices for stress and strain. Now, we have 6 component of stresses. So if I write it down, sigma xx is equal to, obviously it will be related to 6 component of strains here. So it is, say, the first constant times epsilon xx plus second constant times second strain component plus third constant times third strain component, which is epsilon zz. Then we have fourth component gamma xy plus fifth constant gamma yz plus the last one gamma xz. Similarly, we can also write down the expression for all 6 stress components, right? Now, if we do that, and if you look at this expression, you can identify how many proportionality constants are there. So here we'll have A21, then epsilon xx plus A22 epsilon yy plus A23 epsilon zz plus A24 gamma xy plus A25 gamma yz plus A26 gamma xz. Likewise, if we complete all these rows, we get the first expression that actually has stress on the left hand side and all strain components on the right hand side. So if we do that, so what we get is basically on the left hand side, we have all stress components and then we have Aij and then we have all strain components, right? And if you look at this matrix, it is a 6 cross 6 matrix, right? Let us quickly go back. So this is the expression, and each row on the right hand side, we have 6 constants. First row has A11, A12, A13, A14, A15, and A16. Similarly, for all other rows, we have same number of constants. So it's a 6 cross 6 matrix. That means there are 36 constants, right? Okay. Now, we'll see as we progress in this course how this assumption of isotropy helps us to reduce this number of constants. That we'll see as we progress. Now, let us assume x, y, z coordinate. So, OX, Y, Z, it coincides with sigma 1, sigma 2 and sigma 3. So, this three components, sigma 1, sigma 2, sigma 3, they are principal stresses, right? Okay. Similarly, we'll have principal strains also, epsilon 1, epsilon 2 and epsilon 3. Now, if we try to correlate these three components of stress and strain, what we get? Sigma 1 is equal to, say, A times epsilon 1 plus B times epsilon 2 plus C times epsilon 3. Because we have principal components and along principal planes, we will not have shear stress and shear strain, right? Okay, so if we slightly modify this expression, so what we have here is A minus B times epsilon 1 plus we have then B times epsilon 1 plus B times epsilon 2 plus C times epsilon 3. Now, because we have isotropic material, obviously B must be equal to C, right? So, we can replace C with B, right? Now, if we do that, we have A minus B times epsilon 1 plus, if we take B common, what we have is within bracket epsilon 1 plus epsilon 2 plus epsilon 3. Now, from our previous discussion, we know that cubic dilation delta V is nothing but epsilon 1 plus epsilon 2 plus epsilon 3. That's the first strain invariant. Therefore, we have sigma 1 is equal to A minus B times epsilon 1 plus we have B times delta, right? So, this is written in a slightly different form because A minus B, this is also a constant. So, we can write it 2 mu epsilon 1 plus delta times lambda. So, we have basically two constants, mu and lambda, right? Similarly, we can also write down sigma 2 is equal to twice mu epsilon 2 plus lambda times delta. And the last one, sigma 3 is equal to 2 mu epsilon 3 plus lambda times delta. So, we have three principal components of stresses and then three principal components of strain, and that we can correlate using two different constants, and these are called Lami's constant. Right? Okay. So, the first thing to remember that if the material is homogeneous, elastic, isotropic, then we can correlate stress with strain using two different constants. Now, if you recall your elementary strength of material, we are familiar with Young's modulus. In fact, the 1D case I showed you in the previous slide, it had sigma and epsilon. They are related. using this constant. This is called Young's modulus, right? Similarly, we have Poisson's ratio, then we have bulk modulus, and then we have shear modulus. So these are the constants we are familiar with. We'll see in today's lecture how we can express all these constants in terms of these two constants, which are called Lami's constants, right? So that we will do further. For that, let us first define the reference frame. So what we have is XYZ. So we have OXYZ. And let us again assume that it coincides with principal stresses sigma 1, sigma 2, sigma 3. Right? Then let us consider another set of coordinate which are defined by these primes. So we have x prime, y prime, and z prime. Now, obviously, if we consider x prime direction, so what we have, OX prime will have direction cosines, so in x1, in y1, in z1. Similarly, OY prime will have in x2, in y2, and in z2. Right? Obviously, as per our definition, OX prime is perpendicular to OY prime. Now, if that is the case, we can easily conclude that nx1 times nx2 plus ny1 times ny2 plus nz1 times nz2 is equal to 0, because these two directions, OX prime, OY prime, they are perpendicular to each other. Okay. Now, in this prime coordinate system, if we define the stress components, so we have sigma x prime, that's the normal stress, and we have shear stress tau x prime, y prime. And these components we can express in terms of sigma 1, sigma 2, sigma 3, and that we have already discussed, right, in our previous lectures. So we have sigma x prime is equal to sigma 1 in x1 square plus sigma 2 in y1 square plus sigma 3 in z1 square. Similarly, tau x prime, y prime will be what? It is sigma 1 in x1 in x2 plus sigma 2 in y1 in y2 plus sigma 3 in z1 in z2. Right? Okay. Now, so this equation is equation number 1 and this is equation number 2. These are the two equations that expresses sigma x prime and tau x prime y prime in terms of principal components sigma 1, sigma 2, sigma 3, right? Similarly, we can also express strains which are epsilon x prime, and that is equal to epsilon 1 in x1 square plus epsilon 2 in y1 square plus epsilon 3 in z1 square. And we have gamma x prime y prime is equal to epsilon 1 in x1 in x2 plus epsilon 2 n y1 n y2 plus epsilon 3 n z1 n z2, right? So this is the third equation, and we have here fourth equation, right? Okay. Actually, there will be, because we have engineering strain here, so there will be 2 times this quantity. Recall, we earlier defined epsilon xy is equal to gamma xy by 2, right? Now, what we can do, we can substitute expression for sigma 1, sigma 2, sigma 3 in this equation, right? So what we have, epsilon 1, epsilon 2, epsilon 3, and we have already defined sigma 1, sigma 2, sigma 3 in terms of epsilon 1, epsilon 2, epsilon 3, right? So let us do that. So what we first do, we consider the normal stress in prime coordinates. So what we have is sigma x prime, and for that we have sigma x prime equal to sigma 1. In place of sigma 1, we can now write the expression that we have using epsilon 1, epsilon 2, epsilon 3, right? So we have sigma 1 in x1 square plus sigma 2 in y1 square plus sigma 3 in z1 square. Okay. And in place of sigma 1, sigma 2, sigma 3, we'll use the expressions here. Okay. Now if you do that and simplify, you can get this expression. So lambda times delta, within bracket we have n x1 square plus n y1 square plus n z1 square plus 2 mu, within bracket we have epsilon 1, then n x1 square plus epsilon 2 n y1 square plus epsilon 3 n z1 square. You can recall the property of direction cosine, so this is equal to 1, right? And also this expression you can easily identify. Okay, we just now derived the expression which is here, okay, in equation 3. So if you further simplify the expression of sigma x prime, what we get is lambda times delta plus we have 2 mu times epsilon x prime. Now look at this expression. In the prime coordinate, we try to find out the expression of sigma x prime, which is the normal stress, and on the right hand side we have normal strain, right? Similarly, we can also write down sigma y prime is equal to, again, lambda times delta plus 2 mu epsilon y prime. And the last one, sigma z prime is equal to lambda times delta plus 2 mu epsilon z prime. Right. Now, what we can do, if we sum up the left hand side, what we have, sigma x prime plus sigma y prime plus sigma z prime is equal to what? We have 3 lambda plus 2 mu. Within bracket we will have epsilon x prime, then epsilon y prime and epsilon z prime, right? And what is this quantity? Epsilon x prime plus epsilon y prime plus epsilon z prime. This is nothing but again the volumetric string, right? That means delta. So ultimately what we get is 3 lambda plus 2 mu times delta. Okay. Now on the left hand side what we have? We have the first invariant. So we can express this in terms of the principal components. So for principal components what we have sigma 1 plus sigma 2 plus sigma 3. This is also the first invariant that we have already derived earlier. And on the right hand side we have 3 lambda plus 2 mu times delta. Right. Okay. Now if we have a special case where we have sigma 1 is equal to sigma 2 is equal to sigma 3, that means along all three principal direction we have same level of stress, and that be P, that is the amount of pressure that we apply. Then what we have, the left hand side will be 3P, and on the right hand side we have 3 lambda plus 2 mu into delta. Now we can express this in a better way. So P by lambda is equal to 3 lambda plus 2 mu divided by 3. So what is P by lambda? P by lambda is basically the pressure divided by the volumetric strain, and that is what we call bulk modulus K. So we have K is the bulk modulus, and K, if we express in terms of Lami's constants, we have 3 lambda plus 2 mu divided by 3. So that's the first relation we get. The expression of bulk modulus in terms of Lami's constants. Okay. Now instead of sigma x prime, if we consider tau x prime, y prime, and again on the right hand side we have sigma 1, sigma 2, sigma 3. Obviously we can replace these three quantities using strain, and if we do that, let us see what we get. So we have tau x prime, y prime, which is equal to sigma 1 times nx1 nx2 plus sigma 2 times ny1 ny2 plus sigma 3 times nz1 nz2. So if we put the expression of sigma 1, sigma 2, sigma 3 and simplify, we get again lambda times delta. Within bracket we have nx1 nx2 plus ny1 ny2 plus nz1 nz2 plus 2 mu. Within bracket we'll have epsilon 1 nx1 nx2 then plus epsilon 2 ny1 ny2 plus epsilon 3 in z1 and z2. It's very simple. You put the expression of sigma 1, sigma 2, sigma 3 and then simplify, you will get this expression. Now, out of that, you can easily identify this quantity we have defined at the very beginning, because OH prime is perpendicular to OI prime. Obviously, we have, this is the relation. That means nx1, nx2 plus ny1, ny2 plus nz1, nz2 is equal to 0. So, if we use that relation, this first term, first bracketed term is equal to 0. What about the second term? So, within the first bracket, we have epsilon 1 times nx1, nx2 plus epsilon 2 times ny1, ny2 plus epsilon 3 times nz1, nz2. Now, what is the expression for that? Again, it is actually gamma x prime y prime. We have a factor of 2 on the right hand side that we can easily merge with the 2 here, right? So, ultimately what we'll get is tau x prime y prime is equal to mu times gamma x prime y prime. This is very important because shear stress on the left hand side is actually related to the shear strain, right? Similarly, what we can do, we can write down the expression for all other shear stress components, but for the time being, if we refer to our elementary strength of material, when we correlate shear stress with shear strain, the constant we have is what we call shear modulus, right? So that is G times gamma x prime y prime, which means mu is equal to G. That is the shear modulus. So we get the second expression in terms of Lami's constant, right? So that's the second expression. Okay. We are left with two more constants, that is Young's modulus and Poisson's ratio, right? For that, again, let us go back to the expression of sigma 1 plus sigma 2 plus sigma 3. This we have already derived, and if I write down the expression, which is delta times 3 lambda plus 2 mu, right? This is the expression we derived when we evaluated the expression of bulk modulus. Okay. Now, again recall, sigma 1 is what? Sigma 1 is equal to lambda times delta plus 2 mu epsilon 1, right? This we have already derived, okay, in the previous slides. Now, from this expression, we can find out what is delta. Delta is nothing but sigma 1 plus sigma 2 plus sigma 3 divided by 3 lambda plus 2 mu. So, if we put this expression here in the expression of sigma 1, what we have? We have lambda times sigma 1 plus sigma 2 plus sigma 3 divided by 3 lambda plus 2 mu, and then we have the second term, that is 2 mu epsilon 1. Okay. Now, this expression we can simplify. I will give you the final expression and leave it as a home task for you. So what we do, we express epsilon 1 in terms of sigma 1, sigma 2, sigma 3. So if you do that, what we get is lambda plus mu divided by mu times 3 lambda plus 2 mu, and then within bracket we'll have sigma 1 minus lambda divided by 2 times lambda plus mu, then within bracket sigma 2 plus sigma 3. So this I leave it as a home task. So you start from this expression and then find out epsilon 1 in terms of sigma 1, sigma 2, sigma 3. Now we are familiar with this expression because from elementary strength of material, again we know what is epsilon 1. Okay, so if we write down that expression, our epsilon 1 is nothing but 1 by E, that is Young's modulus, within bracket sigma 1 minus nu, that is the Poisson's ratio, times sigma 2 plus sigma, right? Okay. Now if we compare this expression with the previous one, we can easily identify the expression of Young's modulus and Poisson's ratio. So the expression of Young's modulus E is equal to mu times 3 lambda plus 2 mu divided by lambda plus mu. How do we get it? Again, I repeat, I compare this expression with the one we derived here. Okay. Now, if you do that, you get the first expression, that is Young's modulus, and the second one is for Poisson's ratio, right? Poisson's ratio is lambda by 2 times lambda plus mu. So what we have done here is Young's modulus and Poisson's ratio we have derived in terms of Lami's constants. That actually completes our derivation. So we have the expression for Young's modulus, Poisson's ratio, bulk modulus and shear modulus, all in terms of two constants, lambda and mu. So if you look at the first expression we started with for stress and strain, we have altogether 36 constants, and the moment we apply the assumption homogeneous, elastic and isotropic, this isotropy actually reduces the number of constants. So we have this expression here. This is called generalized Hooke's law. Okay. So let me write here. This is the and the moment we apply the assumptions here, we actually reduce 36 constants into two constants, that is lambda and mu, and we get the expression for Young's modulus, Poisson's ratio, bulk modulus and shear modulus. Okay. So now we can use these two Lami's constants here, and then within this homogeneous, elastic and isotropic framework, we can now correlate stress and strain very easily using these two constants. Okay. And using these two constants, we express all these other constants that we are familiar with. So with that, let us close here. We'll continue our discussion, and then first we'll find out the relation between stress and strain. We'll write down the expression, and then further we will see how from stress we can quantify strain and vice versa using these material constants that we'll discuss in our next class. Thank you very much.